We fixed our gaze 40,000 years into the future. We calculated Voyager 2's epic flyby of the star Ross 248. We even calculated its visit to Sirius 296,000 years from now. But we were all looking in the wrong place. Ironically, the final destination for Voyager 2 isn't tens of thousands of years away. That place is right here, and that time is now. The spacecraft has been travelling for 50 years, but the end of its mission will come in just the next 10 years. Losing 4 watts of power each year, this technological marvel will fall silent 21 billion kilometres away, at the very doorstep of the solar system. But even that is not the most incredible part. The real question is, what will remain when that final signal is cut? If you too want to learn the secret behind this cosmic farewell, then like the video. Because the answer we seek is revealed not by looking to the farthest reaches, but to the closest. We begin. For years, we imagined space probes would travel forever. Immortal explorers crafted from metal, time capsules gliding through the infinity of the universe. This romantic notion isn't entirely true. One of humanity's greatest achievements, Voyager 2, has an end. Its power is running out. It is slowly dying. And when this death occurs, it will be in a very special place in the galaxy. This is why, before that final moment arrives, we must understand the journey of this machine. Its story is, in fact, our story. To understand the journey of Voyager 2, you first have to grasp its scale. Its current speed is about 55,000 kilometers per hour. That sounds incredible, dozens of times faster than a bullet. On the scale of the universe, this is a snail's pace. At this speed, Voyager 2 needs a full 18,000 years to cover just 1 light year. Right now, it is 21 billion kilometers away from us. This distance is about 140 times the distance between the Earth and the Sun. That is why a light signal from it takes more than 19 hours to reach us. When engineers send a command, it takes almost 40 hours for the signal to get there and the response to come back. Think about it. You ask a question, and you get the answer 2 days later. This incredible distance and this cosmic slowness are the fundamental realities that define Voyager 2's destiny. Because its destination is not as far as we thought. But that's not the most interesting part. What's truly interesting is how this slow and lonely journey became so efficient. The secret lies in a mission called the Grand Tour. Voyager 2 was launched on August 20th, 1977, 16 days before its twin, Voyager 1. But this date was not chosen randomly, because on that date, a very rare alignment of the outer planets was occurring. Jupiter, Saturn, Uranus and Neptune had entered such a configuration in the sky that a single spacecraft could visit them all. This event occurs only once every 176 years. This is why NASA could not miss this opportunity. The core logic of the mission was the gravitational slingshot effect. As Voyager 2 passed by each planet, it would use its massive gravity like a slingshot. The planet's gravity would both accelerate the probe and bend its trajectory, flinging it toward the next target. Without this ingenious plan, visiting all 4 planets could have taken decades and required enormous amounts of fuel. But, thanks to this cosmic slingshot, almost no fuel was spent. Humanity had bought a ticket to the outer suburbs of the solar system. So, what did it see at the first stop with this ticket? Voyager 2 reached Jupiter in July 1979, and the view it encountered changed the history of planetary science forever. Because until then, we thought moons were boring, dead pieces of rock. But Voyager showed us we were wrong. It discovered active volcanoes on Jupiter's moon Io. This was the first place beyond Earth where active volcanism was found. Another moon, Europa, had a smooth, icy surface covered with cracks. This image sparked the idea that there might be a vast ocean beneath the ice, perhaps an ocean harbouring life. The ancient crater-filled surfaces of Ganymede and Callisto told us a story spanning billions of years. Jupiter itself was also a surprise. It confirmed that the great red spot in its atmosphere was a giant storm. This storm was even larger than Earth. This is why Jupiter was not just a gas giant, but a dynamic, living system. Every single photograph, every single data packet sent by Voyager 2 was rewriting textbooks. But this was only the beginning. When Jupiter's slingshot effect launched the probe towards Saturn, no one expected the secrets of the ringed planet to be so complex. The arrival date at Saturn was August 1981, and Voyager 2 focused on the planet's most iconic feature, its rings. What appeared from Earth as a few thick rings was actually composed of thousands of individual ringlets. These incredibly thin ringlets, made of ice particles, were arranged like grooves on a record, with gaps between them. This unbelievably complex structure baffled scientists, because no one knew how such an orderly and delicate structure could have formed. The probe also studied Saturn's atmosphere. Wind speeds reached 1,600 kilometers per hour. This was many times faster than the most powerful hurricanes on Earth. Voyager 2 also passed by Saturn's moons. It gave a distant nod to Titan, the main target of its twin, Voyager 1. This visit to two giant planets was an achievement in itself, more than enough for one mission. But for Voyager 2, this was only halfway, because the strangest, coldest, and most unknown worlds of the solar system awaited it. What would it find in that icy darkness, billions of kilometers away? The answer was stranger than anyone could have possibly imagined, because Voyager 2 was now heading toward a planet lying on its side, and that planet, the next stop after Saturn, was Uranus. Voyager 2 reached this mysterious world in January 1986, almost 5 years after leaving Saturn, and this was a first in history. Because, until then, no human-made object had visited Uranus, and to this day, no other has gone. The site it encountered was a complete anomaly. While other planets spin like a top, Uranus was like a rolling ball, because the planet's axis was tilted a full 98 degrees relative to its orbital plane. This meant the planet was lying on its side. This is why Uranus rolled around the Sun like a barrel. The result of this strange situation was even stranger. Each of the planet's poles received continuous sunlight for a full 42 years, followed by a 42-year plunge into pitch darkness. Voyager 2 discovered 10 new moons of this bizarre world, but the biggest shock came when it measured the planet's magnetic field. The magnetic field was tilted 60 degrees with respect to the planet's rotation axis, and it was also offset from the planet's center. This created an asymmetric and strange magnetosphere, never before seen on any planet. Uranus was an exception that broke the rules of the solar system. This journey would show that exceptions might actually be the rule, because the next target was Neptune. Voyager 2 arrived at its final planetary stop in August 1989, a full 12 years after its launch, and again, all expectations were overturned. Neptune was so far from the Sun that it received less than 1% of the sunlight that Earth receives. This is why scientists expected it to be a cold, calm, and boring world. But what Voyager 2 saw was a stormy and dynamic hellscape. In the planet's blue atmosphere, it discovered a giant storm system, similar to Jupiter's Great Red Spot, but darker in colour, the Great Dark Spot. And the wind speeds were at unbelievable levels. Winds exceeding 1,900 kilometers per hour were measured. These were the fastest winds ever detected in the solar system. Voyager 2 revealed the details of the planet's rings and discovered 6 new moons. The fact that it could be so active with so little energy proved that Neptune had a strong internal heat source. Even the most distant planet in the solar system had a boiling energy within. But the real star in the Neptune system was not the planet itself, but its largest moon. And this moon defied everything known. This moon was Triton, and Triton was the most rebellious moon in the solar system, because while almost all planets and moons rotate in the same direction, Triton rotated in the opposite direction. This is known as a retrograde orbit. This fact was the biggest proof that Triton did not form with Neptune, but was a dwarf planet captured from the Kuiper Belt later on. It was like a stranger forced into the system. But the oddities didn't end there. Voyager 2 discovered active geysers on Triton's surface. These geysers, which spewed nitrogen gas up to 8 kilometers high, made Triton the second object known to be geologically active in the outer solar system after Io. Moreover, it did this on one of the coldest surfaces ever measured in the solar system. The temperature was minus 235 degrees Celsius. How such a cold body could be so active is a mystery that is still not fully understood today. Triton was a treasure trove for planetary science, but this was Voyager 2's last stop. Neptune's gravity gave the probe one final slingshot, and it flung it below the plane of the solar system into the darkness of interstellar space. Jupiter's volcanoes, Saturn's thousands of rings, Uranus's tilted axis, Neptune's supersonic winds and Triton's ice geysers. Voyager 2 had shown humanity how diverse, how strange, and how vibrant the solar system was. 4 planets, dozens of moons, and countless discoveries. The mission could have ended here, but it didn't, because the real mission was just beginning. The planets were just stops along the way. The main target was the boundary itself, that invisible line where the sun's influence ends and the interstellar ocean begins. Voyager 2 was now heading toward that line, but what instruments inside a spacecraft could detect this invisible boundary? Which sensors could tell us that we had left the sun's kingdom? Because this new journey wasn't about taking pictures. This journey was all about feeling. And that feeling came suddenly after years of travel. It was like hitting a wall. But this wall was invisible. It was not physical. And now comes the real shock. Because Voyager 2 had found the end of the solar system. This was much more than a discovery. This was reaching a boundary. And what they saw at that boundary was of a kind that would shake everything we knew. The first shock was called the termination shock. It shouldn't have happened, at least not so clearly. It occurred in August 2007, about 12.5 billion kilometers from the Sun, at a distance of 84 astronomical units. Until that moment, the solar wind, the stream of charged particles flowing from the Sun, was traveling at a supersonic speed of about 1.1 million kilometers per hour. But then it suddenly slowed down. Just like a fast-moving car on a highway hitting a traffic jam, the speed abruptly dropped to 400,000 kilometers per hour. This sudden braking heated the plasma to an incredible degree. The temperature skyrocketed from about 5,500 degrees Celsius to nearly 550,000 degrees Celsius in an instant, within just a few hours. The magnetometer detected that the magnetic field, which had been orderly until then, suddenly became turbulent and chaotic. This was the place where the sun's wind first felt the back pressure of the interstellar medium, the first point where the sun's breath was taken away. But this wasn't the boundary itself. This was just the beginning of the boundary. This was the buffer zone between two kingdoms, and Voyager 2 was now entering that dangerous and unknown region. This region is called the heliosheath, and Voyager 2 had to spend more than 10 years here, because this region was much more complex and chaotic than predicted. This was a turbulent hell, where the slowed but not yet stopped solar wind accumulated, compressed, and heated up. The thickness of this region was between 6 and 7.5 billion kilometers, about 40 to 50 astronomical units. Voyager 2 swam in this chaotic sea for 10 years. The plasma measurements showed that the solar wind was never calm here. Sometimes the flow was orderly, sometimes it was incredibly turbulent. The magnetic field was constantly changing direction, twisting, almost tying itself in knots. Scientists couldn't fully explain this chaos. Computer simulations suggested that this region might be filled with what are called magnetic flux ropes, intertwined magnetic field lines. These ropes would merge, separate, and create the turbulence observed by Voyager 2. The cosmic ray detector noticed something even stranger. The intensity was constantly increasing, but this increase was not smooth. It would suddenly drop, then rise again. A powerful burst from the sun would temporarily push this boundary outward, blocking cosmic rays for a while. The heliosheath was a living, breathing, constantly changing boundary, and Voyager 2, after traveling inside this monster for 10 years, finally reached the true boundary. And that was the moment everything changed. November 5th, 2018, about 18 billion kilometers from the sun, 120 astronomical units. The plasma instruments suddenly fell silent. More accurately, what they were measuring suddenly vanished. The solar wind. It completely disappeared. Within a few hours, that stream of particles flowing outward at 400,000 kilometers per hour simply stopped. It zeroed out. This seemed impossible, because a wind doesn't just stop like that. But it did. In its place, a much slower, much colder plasma moving in a completely different direction appeared. This was the plasma belonging not to the Sun, but to the galaxy itself. This was interstellar plasma. The temperature dropped from 550,000 degrees to about 33,000 degrees. The density, surprisingly, increased slightly, because the solar wind had thinned out by expanding outward, whereas the interstellar medium, though sparse, had a more stable density. Voyager 2 had exited the Sun's protective bubble, the heliosphere. It was now in interstellar space. Its twin Voyager 1 had done this 6 years earlier, but its plasma instrument was broken. This is why the first human-made object to directly measure, to taste, to feel the texture of the interstellar medium was Voyager 2. We had crossed the border. We were now outside the kingdom of our home star. Voyager 2 was now encountering particles not from the Sun, but from other stars, from supernova explosions, from the general background of the galaxy. This was its new universe, where it would travel for the rest of its operational life, and for tens of thousands of years after. The sudden blow of the termination shock, the 10-year chaos of the heliosheath, and the sharp silence of the heliopause. These three discoveries proved how dynamic and unexpected the boundaries of the solar system were. But after entering this new environment, the real questions emerged. What exactly did this interstellar ocean look like? What was its magnetic field like? What particles did it carry? And more importantly, how was this old machine from the 1970s finding its way in this alien sea, sending this data back to us? Because the real miracle of Voyager 2 was not just that it went, but that it continued to talk. And the technology that enabled this conversation was a legend in itself. Because Voyager 2 carried a suite of 10 different scientific instruments, and each of these instruments was a pinnacle of 1970s technology. They were the senses that spoke the different languages of space. Thanks to them, we were able to decipher the secrets of the planets and interstellar space. Perhaps the most famous of these instruments was the imaging system. It consisted of two cameras, a wide-angle and a narrow-angle camera. These cameras, instead of modern digital sensors, used a technology called Vidicon tubes. It was state-of-the-art for its time, but now it is completely obsolete. These cameras captured those iconic images of Jupiter's Great Red Spot, Saturn's rings, Uranus's moons, and Neptune's Great Dark Spot. The images were sent to Earth line by line. Transmitting a single frame took minutes, even hours, depending on the spacecraft's distance. Each pixel crossed billions of kilometers of void to reach us. But Voyager 2's eyes were not just its cameras, because in interstellar space there wasn't much to take a picture of. What was truly important were the instruments that measured the things that couldn't be seen, and the most critical of these instruments was the plasma science instrument. This device measured the density, temperature, and speed of charged particles in space. This was the hero that allowed us to detect the heliopause crossing. Throughout its journey, it measured the solar wind, and it was the one that detected when the solar wind disappeared and was replaced by interstellar plasma. The magnetometer measured magnetic fields. It was the one that noticed Jupiter's massive magnetic field, the tilted fields of Uranus and Neptune, and that sharp change in the magnetic field direction at the heliopause. These two instruments worked like a compass and a thermometer, giving Voyager 2 the ability to navigate the interstellar ocean and understand its surroundings. But space wasn't just made of plasma and magnetic fields. It was also filled with invisible and dangerous radiation. The device that measured this radiation was the cosmic ray detector. Its job was to count high-energy particles coming from deep space. These cosmic rays were mostly protons and heavier atomic nuclei, accelerated to near light speed by energetic events in the galaxy, such as supernova explosions or pulsars. The detector measured how many cosmic rays hit the spacecraft and what their energies were. This helped scientists understand the radiation environment in interstellar space. This instrument recorded that sudden and dramatic increase in the cosmic ray count at the heliopause, because once the Sun's protective shield was gone, galactic bullets began to bombard the spacecraft. The low-energy charged particle detector studied lower-energy electrons and ions. These two devices showed us the different faces of radiation. One measured the fast bullets from afar, while the other measured the slower particles in the immediate vicinity. This allowed us to paint a complete picture of the plasma environment, but Voyager 2's senses were not limited to just feeling particles. It also listened to the music of the universe. The Planetary Radio Astronomy instrument detected radio emissions from planets and the interstellar medium. Jupiter emits powerful radio bursts produced by its magnetic field. This instrument helped map Jupiter's magnetosphere by detecting these bursts. The ultraviolet spectrometer measured ultraviolet light from stars and planets. This allowed it to analyze the composition of the outer planets' atmospheres by measuring which wavelengths of light the gases absorbed. The infrared spectrometer measured infrared radiation, essentially heat. This allowed us to determine the temperatures of planetary atmospheres and surfaces. The photopolarimeter measured the polarization and intensity of light to study the structure of planetary rings and atmospheres. And finally, the radio science subsystem used the spacecraft's own radio transmitter as an instrument. By measuring how the spacecraft's signals were bent by planetary atmospheres, they were able to derive profiles of atmospheric density, temperature, and pressure. These 10 instruments made Voyager 2 the most capable explorer of the solar system. Each was a different sense, a different ability. But time took some of these senses away from it. The photopolarimeter failed in 1991. The ultraviolet and infrared spectrometers were turned off to conserve power. But the magnetometer, the cosmic ray subsystem, and the plasma wave subsystem are still working, still sending data, still making discoveries. But how does this machine, which has been traveling in the harsh conditions of space for almost 50 years, keep such sensitive instruments operational? How does it accomplish so much with so little power? Because the real secret is not in the instruments, but in the energy that gives them life. And that energy source is both a miracle and a countdown timer. But what is behind all this? How is it that a machine launched almost 50 years ago, from 21 billion kilometers away, is still talking to us? Now let's get technical, because behind Voyager 2's incredible endurance lies both an ingenious simplicity and an inevitable end. That energy source, the heart of the spacecraft, is also its death warrant. Voyager 2's power comes from its radioisotope thermoelectric generators, or RTGs. These devices were designed to produce electricity in an environment far from the Sun, where solar panels would be useless. The working principle is surprisingly simple and reliable. Inside the RTGs is a radioactive isotope called plutonium-238. As this isotope decays, it emits alpha particles. Alpha particles are actually helium nuclei, consisting of 2 protons and 2 neutrons. When these particles are emitted, they carry kinetic energy, and this energy turns into heat as it collides with surrounding atoms. The plutonium dioxide pellets inside the RTG are therefore incredibly hot. Their temperature reaches about 650 degrees Celsius. This heat flows outward through devices called thermoelectric couples. These couples are made by joining 2 different semiconductor materials. When one side of a thermoelectric couple is hot and the other side is cold, a voltage is created at the junction. When you connect thousands of thermoelectric couples in series, you get enough electricity to power the spacecraft. The cold side is connected to radiator fins, which radiate excess heat into space. This temperature difference between the hot plutonium pellets and the cold radiators generates electricity. But this system has a weak point. Its efficiency is very low, only about 6 to 7%. This means that most of the heat produced by the plutonium is wasted, radiated into space without being converted to electricity. However, what makes RTGs so special is not their efficiency, but their reliability. Because they have no moving parts, there are no mechanisms to wear out or break down. As long as the plutonium decays, the RTG produces power. But that word decay is the key to everything. Because plutonium-238 has a half-life, and that period is exactly 87.7 years. This means that every 87.7 years, the amount of plutonium inside is halved. So after 87.7 years, only half of the original plutonium remains, and it produces only half as much heat. After another 87.7 years, only a quarter remains. This decay follows a mathematically predictable curve. As the plutonium decays, the RTGs produce progressively less power. When Voyager 2 was launched, its RTGs produced about 470 watts of electricity. This was enough to run all systems and leave some backup power. The spacecraft's instruments, computers, radio transmitter, and heaters all drew power from the RTGs. But when it crossed the heliopause in 2018, after 41 years, the power produced by the RTGs had dropped to about 250 watts. That's almost half of its original power gone. And the power output continues to decrease by about 4 watts every year. This may not sound like much, but it adds up over the decades. Each year, the spacecraft has 4 fewer watts of power available. Every 10 years, 40 fewer watts. This is why engineers have been fighting a war with this dwindling power for years. It's like trying to cross the ocean with a leaky bucket. They have to conserve every drop of energy, and this conservation requires painful sacrifices. The first of these sacrifices was turning off the heaters. This was a huge risk taken to continue the mission. Some parts of the spacecraft were designed to operate at or slightly below room temperature. But now, with the heaters turned off, these parts are operating at sub-zero temperatures, even much colder. This can cause materials to become brittle in the cold, lubricants to freeze, and electronic components to behave unexpectedly. But Voyager 2 has shown incredible resilience. Systems that were never designed to work in such cold are still functioning. This shows both the quality of the engineering and, perhaps, a bit of luck. The second sacrifice was shutting down non-critical instruments. Since there was nothing left to photograph after the Neptune encounter, the imaging cameras were turned off. The ultraviolet and infrared spectrometers were disabled to save power. The photopolarimeter had already failed in 1991 and could not be restarted. The remaining working instruments were those studying the space environment, the magnetometer, the cosmic ray subsystem, and the plasma wave subsystem. Because these instruments were still scientifically valuable, they were measuring the interstellar medium, and there was no other spacecraft doing that. But even their end is approaching. To conserve every single watt of energy, even the spacecraft's computer was reprogrammed. Engineers rewrote the software to reduce the computer's processing load. They adjusted the data collection and transmission timing to minimize power consumption. They shut down redundant systems that were no longer needed. Every single watt was carefully managed, squeezed, optimized. Despite all these efforts, the available power continues to decline. This is an unavoidable fact. By the year 2026, Voyager 2 had only its last 3 instruments left: the magnetometer, the plasma wave subsystem, and the cosmic ray subsystem, which is scheduled to be turned off in 2026. The instruments will be turned off one by one. The first instrument to be shut down will probably be one of the particle detectors, then another, then another. By the mid-2030s, the spacecraft will likely not have enough power to run any instruments. Each shutdown will mark another step toward the end of the mission. The last systems to be shut down will likely be the radio transmitter and receiver. As long as the spacecraft has enough power to run the radio, engineers on Earth can still communicate with it, even if it can't collect scientific data. The radio link is the spacecraft's last connection to Earth. the last thread connecting it to the world that built it. But eventually, probably in the late 2030s or early 2040s, the power output will drop below the minimum level required to run the radio. The transmitter needs about 23 watts to operate. In addition, power is needed for the computer that formats the data and controls the transmission. When the RTGs can no longer supply that much power, the radio will fall silent. What exactly will happen when that moment comes? What will the engineers on Earth feel when they receive the last signal? And after that moment of silence, will Voyager 2's journey really be over? Because the end of power may not mean the end of the journey. On the contrary, it could be the beginning of a completely new and infinite journey. The journey of a ghost ship. And when that moment comes, when the radio falls silent, it will not be the end of everything for Voyager 2. On the contrary, the real journey will begin then. Because, from that point on, Voyager 2 will be left completely on its own. A ghost ship, completely inert, a pile of metal and electronics, unable to communicate, unable to collect data, unable to respond to commands from Earth. Its instruments will be dark, its computer will be frozen, and its radio transmitter will no longer be able to produce the signal that has connected it to Earth for decades. From that moment on, Voyager 2's fate will be entirely at the mercy of orbital mechanics and the gravitational influence of nearby stars. It will continue to glide on its trajectory with nothing to slow it down. Because, in the vacuum of interstellar space, there is no air resistance, no friction. This is why there are no forces to reduce its momentum. At its speed of about 55,000 kilometers per hour, unless it collides with an object, it will essentially continue to move forever. But what if it does collide? The probability of a collision in interstellar space is extraordinarily low. To understand this, you need to grasp the emptiness itself. This medium between the stars contains on average only one atom per cubic centimetre. This is much sparser than even the best vacuum we can create in laboratories on Earth. For comparison, the air you are breathing now contains about 25 quintillion molecules per cubic centimetre. So interstellar space is roughly 25 quintillion times less dense than the air you breathe. To visualize this emptiness, consider this. If you took all the matter in a cubic light-year of space and compressed it to the density of Earth's atmosphere, it would fit into a volume smaller than a grape. This is why Voyager 2 could travel for billions of years without hitting anything larger than a microscopic dust particle. But what about those microscopic dust particles? Aren't they a threat? At 55,000 kilometers per hour, couldn't even a small particle cause significant damage? Actually, not really, because this speed is quite slow on a cosmic scale. Meteors entering Earth's atmosphere strike at speeds ranging from 40,000 to 250,000 kilometers per hour. But what burns them up is not so much their speed, but the friction in the atmosphere. In interstellar space, there is no atmosphere to create friction. This is why a dust particle hitting Voyager 2 would only create a small pit on the surface it strikes. Perhaps a crater a fraction of a millimeter deep. Over millions of years, the spacecraft might accumulate thousands or even millions of these small impacts. Its surface might become pockmarked with craters and scars, but this damage would remain superficial. Its main structure would not be compromised, because its electronics are safe inside the body, protected by aluminium and other materials. A microscopic dust particle cannot penetrate deep enough to damage critical systems. So what about larger objects? Asteroids, comets, rogue planets? Yes, such objects do exist in interstellar space. They might have been ejected from planetary systems by gravitational interactions, but they are also incredibly rare. Some estimates suggest there could be trillions of rogue planets in our galaxy, but when you consider the vast volume of the galaxy, even this number is very small. Our galaxy is roughly 100,000 light-years across and has a volume of about 100 quadrillion cubic light-years. If there are a trillion rogue planets, this means there is only one planet for every 100 cubic light-years. The probability of the approximately 3-meter wide Voyager 2 hitting a target in this volume of hundreds of trillions of kilometers is practically zero. This is why, except for an extraordinarily unlikely collision with a large object, Voyager 2 will continue to drift in space indefinitely. But this drift is not an entirely aimless one, because it has a destination. More precisely, its trajectory will take it to a series of rendezvous, and the first of these rendezvous will happen in about 40,000 years. In about 40,000 years, Voyager 2 will make a flyby of a star called Ross 248. This is a longer period than all of recorded human history. At the end of this time, the spacecraft will pass the star at a distance of about 1.7 light-years. This distance might sound very far. 1.7 light-years is roughly 16 trillion kilometers. This is about 3,600 times the distance between the Sun and Neptune. But, on an interstellar scale, this is a fairly close pass, because the average distance between stars in our region of the galaxy is 4 to 5 light-years. So Voyager 2 will pass by Ross 248 at a distance of less than half the average interstellar distance. Of course, by then, Voyager 2 will not be operational. Its power source will have died out tens of thousands of years earlier, and this encounter will be completely passive. At a distance of 1.7 light-years, the gravity of Ross 248 is incredibly weak. This is why the star will have almost no measurable effect on Voyager 2's trajectory. The spacecraft will glide past the star almost unaware of its presence and continue its journey in the galaxy. But that's not the exciting part. Ross 248 is just the first stop, because on Voyager 2's cosmic calendar there is a second rendezvous with a much brighter, much more famous star, and that encounter will happen at the end of a much longer journey. And now comes the real miracle, because long after Ross 248, when the calendars show approximately 296,000 years from now, Voyager 2's path will cross with Sirius. Yes, the Sirius we know, the brightest star in Earth's night sky. This is no longer an ordinary rendezvous. This is like meeting a rock star. But this encounter tells us a much deeper truth about Voyager 2's future. Because, by then, we begin to understand just how uncertain the spacecraft's trajectory will become. This pass by Sirius is not an end, but the beginning of an infinite uncertainty. And now we reach the climax. Because, why does this uncertainty make it impossible to predict the spacecraft's fate? Because Sirius is not a single star, it is a binary star system. The bright star we see is Sirius A, a blue-white giant about twice the mass of the Sun. But orbiting it is a faint white dwarf companion named Sirius B. Sirius B is the remnant of a star that was once larger than Sirius A, but exhausted its nuclear fuel and collapsed. These two stars complete an orbit around each other every 50 years. During this orbit, the closest they get to each other is 8 astronomical units. That's about the distance between the Sun and Saturn. The farthest they get is 31 astronomical units. That's the distance between the Sun and Neptune. This means a dynamic and constantly changing gravitational dance. Voyager 2 will pass this system at a distance of 4.3 light-years in about 296,000 years. This distance is roughly equal to the distance between the Sun and our nearest star, Proxima Centauri. This is why the effect of the Sirius system on Voyager 2's trajectory will still be very weak. The gravitational pull will be negligible. But this encounter shows us something else, how dynamic the universe is. Because the real problem is that stars are not fixed. They are also moving. Just like the Sun, each one is orbiting the galactic center in its own path. Some move fast relative to the Sun, some slow. Some are moving toward us. Some are moving away from us. Over tens of thousands of years, these stellar motions completely change the relative positions of the stars. A star that is now far from Voyager 2's path might be right on its path in 100,000 years. Or a star that is now nearby might be long gone by then. This is why calculating Voyager 2's trajectory millions of years into the future requires knowing the positions and velocities of hundreds of nearby stars. And even the smallest uncertainties in these positions and velocities accumulate over time, making the long-term trajectory increasingly uncertain. Astronomers can say with reasonable certainty where Voyager 2 will be in 50,000 or 100,000 years, but predicting where it will be in a million years involves significant uncertainty. Predicting 10 million years from now is little more than a guess. The spacecraft's trajectory becomes mathematically chaotic. Small changes in initial conditions lead to large differences in outcomes over time. This doesn't mean the spacecraft's motion is random. The motion is still governed by Newton's laws of motion and gravity. But it does mean that long-term predictions become unreliable. Despite this uncertainty, we can make some general statements about Voyager 2's future. Over millions of years, Voyager 2 will have many such encounters with stars. Each encounter will slightly alter the spacecraft's trajectory, bending its path this way and that. Some encounters will speed the spacecraft up a bit, others will slow it down. These small changes will accumulate over time, making the spacecraft's long-term trajectory increasingly uncertain. This is similar to how the motion of the planets in the solar system becomes chaotic over very long timescales. We can predict where Earth will be next year with extraordinary precision. We can predict where it will be in 1,000 years with good accuracy. But predicting where Earth will be in 100 million years is much harder. Voyager 2's motion in the galaxy faces the same challenges, but one thing we know for sure: Voyager 2 will continue to orbit the galaxy, along with the Sun and all the other stars in the Milky Way, because the spacecraft is gravitationally bound to the galaxy. It is not moving fast enough to escape the galaxy's gravitational pull, so it will remain in the Milky Way. Over hundreds of millions of years, Voyager 2 will complete its own orbit around the galactic center. The Sun's orbital period is about 225 million years. Voyager 2's orbital period will be different, but it will be in the same general range. So what will ultimately end Voyager 2's journey? Not a collision, probably. Not running out of momentum, because there is nothing to slow it down. The answer is surprising. Voyager 2 will likely continue to drift through the galaxy for billions of years, until the galaxy itself changes so much that the concept of the spacecraft's orbit becomes meaningless. And this change will begin in about 4 billion years. The Milky Way galaxy will collide with our neighbour, the Andromeda galaxy. These two giant galaxies will merge over a period of a few billion years, forming a new, larger galaxy. During this merger, the stars will be scattered by the gravitational chaos of the collision, their orbits randomized. Voyager 2 will also be caught in this chaos. Its orbit will be completely changed by the gravitational influence of passing stars and the overall restructuring of the galaxy. The spacecraft will likely survive the merger physically because the distances between stars are so great that even during galaxy mergers, actual collisions between stars are rare. But its orbit will be completely scrambled. It will be sent into a completely new orbit in the merged galaxy. Beyond that, we are talking about such long timescales that other processes also become important. Over trillions of years, stars will exhaust their fuel and die out. The Sun will become a white dwarf, slowly cooling over tens of billions of years to become a black dwarf. Other stars will do the same. Eventually, the galaxy will be filled mostly with dead stellar remnants, white dwarfs, neutron stars, black holes, and a few long-lived red dwarfs that are still burning their fuel. Voyager 2 will continue to drift among these dead stars, a silent artifact from a civilization that existed trillions of years ago. But even this is not the end, because the universe itself is heading toward a much stranger end, and Voyager 2 will witness that end as well. That end is called gravitational radiation. This will be the end of everything. Any object in an orbit emits gravitational waves, which are ripples in space-time that carry away energy. This energy loss is immeasurably small for normal objects. But over unimaginable timescales like 100 quintillion years, this effect accumulates. The stars, planets, and spacecraft orbiting the galactic center will slowly spiral inward as they lose energy to gravitational radiation. Voyager 2 will also eventually spiral into the galactic center, along with everything else. But 100 quintillion years is such an unimaginably long time that it's hard to even describe. That's a 1 followed by 20 zeros. The universe is currently only 13.8 billion years old. 100 quintillion years is about 7 billion times the current age of the universe. This is no longer a physical journey, but a philosophical existence. But in that existence, Voyager 2 is not alone, because it carries with it humanity's greatest hope, greatest dream, and greatest message. And that message is hidden on a golden record. That record may survive even longer than Voyager 2 itself, and that record is the golden record. Perhaps the most famous and poetic aspect of the Voyager missions, because both Voyager spacecraft carry a 30-centimeter gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. This project was led by a committee chaired by the famous astronomer and science communicator Carl Sagan. Sagan and his team's task was almost impossible. How do you fit the entire Earth, all of humanity, all our history and culture onto a single record? What do you include? What do you leave out? How do you explain who we are to someone who might have completely different senses, different ways of thinking, different concepts of reality? This was writing the most challenging summary in human history. This is why the team decided to include a variety of content to cover as many aspects as possible. The record contains greetings in 55 languages, from ancient Sumerian and Hittite to modern Mandarin, English, and Swahili. Each greeting is a short message of just a few sentences, but together, they represent the linguistic diversity of humanity. Some greetings are formal, others are friendly. Some express hope for peace. Others simply say, "Hello." This was humanity's first cosmic hello. Not just one voice, but 55 different voices. But Earth was not just about humans. This is why the record also includes the sounds of nature. Thunder, the howl of the wind, the sound of rain, waves crashing on a shore, a waterfall, a stream. Bird chirps, whale songs, the trumpeting of elephants. These sounds were intended to convey the richness of Earth's natural environment, the diversity of life and ecosystems. This was the symphony of our planet. The record also contains the sounds of human activities: footsteps, heartbeats, laughter, a crying baby, a kiss, a mother's first words to her newborn child, tools being used, a saw cutting wood, a hammer striking metal, vehicles, a horse-drawn cart, a train, a car, a plane taking off. These sounds were intended to show how humans interact with their environment, how we use tools, how we travel, and of course, music. Music from various cultures and time periods was selected. Bach, Beethoven, Mozart, representing Western classical music. Chuck Berry's Johnny B. Good, representing rock and roll. Traditional music from Java, Peru, Zaire, India, Japan, and other cultures. This selection was intended to show the diversity of human musical expression. Each piece of music was chosen to represent a different aspect of human creativity, different emotions, different cultural traditions. This was a playlist of the human spirit sent to the universe, but the record wasn't just sounds, it was also a picture gallery. The record contains 116 images showing scenes from Earth, mathematical and physical constants to provide a universal frame of reference, diagrams of the DNA structure, cell division, human anatomy, landscape pictures, mountains, oceans, deserts, forests, pictures of animals, insects, fish, birds, reptiles, mammals, pictures of people from various cultures, showing different activities, different ages, different environments, architectural pictures, from ancient structures to modern cities, pictures of technology, like scientific instruments, spacecraft. These images were encoded as analog signals. Each image was converted into a waveform that could be etched into the grooves of the record. To decode the images, you need to understand the encoding scheme. The instructions to do this are etched onto the cover of the record. These instructions use a symbolic language that tries to be as universal as possible. It shows the basic principles of the encoding, the scan rate, the number of lines per image. It assumes the finder has some understanding of mathematics and physics, but tries not to make too many assumptions about their specific knowledge or abilities. This was the most complex user manual ever sent into the universe, and this manual contained humanity's greatest secrets. So how will this record withstand a journey of billions of years? The record is housed in a protective aluminium cover, designed to protect it from radiation, micrometeoroid impacts, and the extreme temperature swings of space. The cover also includes a cartridge and needle for playing the record. The record itself is gold-plated to prevent corrosion, because gold is chemically inert and will not oxidize or rust, even over billions of years. The images and sounds are encoded as analog waveforms etched into the grooves of the record, just like a vinyl record. As long as the physical structure of the record remains intact, the information is theoretically recoverable. The record also contains a sample of uranium-238 in a pure form. This was included as a kind of radioactive clock. The half-life of uranium-238 is 4.5 billion years. By measuring how much of the uranium has decayed into lead, a finder of the record can determine how long ago it was created. This will tell them roughly when the Voyager mission took place, even if they can't decipher any of the other information on the record. This was a date of manufacture label left for the universe. This incredible engineering marvel, this cosmic message, this immortal artifact, accompanies Voyager 2 on its endless journey. But all this effort, all these details, all these hopeful messages. So what does this mean for us? What was the real philosophy behind such a massive effort? Now is the time to stop and think. Because the story of the Golden Record tells us much more than just about communicating with aliens. This story is actually about us. The greatest story we tell ourselves. But now is the time to stop and think. Because the real purpose of the Golden Record was never to communicate with aliens. Everyone knew how low the chances were. Space is too big. The spacecraft is too small. The record was actually a statement to ourselves. It was the idea that humanity could create something that might outlive our civilization, our planet, even our sun. It was a message in a bottle, thrown into the cosmic ocean, sent not with the expectation of being found, but as an expression of hope and curiosity, a symbol of the human desire to reach beyond our limits. And now we face the most important question. What does this machine, launched almost 50 years ago and now drifting in interstellar space, tell us about our own place? The answer to this question begins with a great paradox. On the one hand, there is the incredible achievement of humanity. We built Voyager 2, we launched it, we guided it to the farthest corners of the solar system, and now it is a man-made object that has entered interstellar space. This is a testament to the intelligence, curiosity, and perseverance of our species. But, on the other hand, there is our absolute smallness in the face of the incomprehensible vastness of the universe. Voyager 2 is travelling at 55,000 kilometers per hour, but it will take it 40,000 years to reach the nearest star, and billions of years to cross the galaxy from one end to the other. This is why there is a tragic reality in this journey. We will never see the end of this journey. Not us, not our children, nor their grandchildren. When Voyager 2 passes by Ross 248, the civilization that built it may already be history. When it reaches Sirius, humanity might not exist on Earth anymore. This is the sadness of sending an emissary into eternity who will never return. But that word "but" changes everything. Because within this smallness, there is an incredible beauty. Yes, we may not be able to physically go to those stars, but with our minds, we are there. Voyager 2 is our eye, our ear, our touch. It travels in that void on our behalf, an extension of our existence. This is why you too, yes you, are a part of this incredible journey. You too are drifting in interstellar space with that small piece of metal. Because what Voyager 2 carries is not just instruments and a golden record. It carries your curiosity, your dreams, your desire to understand the universe. We are touching the universe through that machine. This is not a victory of our power, but of our understanding. And this confronts us with a second paradox: time itself. On the one hand, there is Voyager 2's journey that will last for billions of years, an almost eternal life. But, on the other hand, there is our fleeting existence. Human life is less than a blink of an eye on the cosmic calendar. When the galaxy merges, when the sun dies, when the last stars burn out, Voyager 2 will still be there, which are ripples in space-time that carry away energy. This energy loss is immeasurably small for normal objects. But, over unimaginable timescales like 100 quintillion years, this effect accumulates. The stars, planets, and spacecraft orbiting the galactic center will slowly spiral inward as they lose energy to gravitational radiation. Voyager 2 will also eventually spiral into the galactic center, along with everything else. But 100 quintillion years is such an unimaginably long time that it's hard to even describe. That's a 1 followed by 20 zeros. The universe is currently only 13.8 billion years old. 100 quintillion years is about 7 billion times the current age of the universe. This is no longer a physical journey, but a philosophical existence. But in that existence, Voyager 2 is not alone, because it carries with it humanity's greatest hope, greatest dream, and greatest message. And that message is hidden on a golden record. That record may survive even longer than Voyager 2 itself, and that record is the golden record. Perhaps the most famous and poetic aspect of the Voyager missions, because both Voyager spacecraft carry a 30-centimeter gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. This project was led by a committee chaired by the famous astronomer and science communicator Carl Sagan. Sagan and his team's task was almost impossible. How do you fit the entire Earth, all of humanity, all our history and culture onto a single record? What do you include? What do you leave out? How do you explain who we are to someone who might have completely different senses, different ways of thinking, different concepts of reality? This was writing the most challenging summary in human history. This is why the team decided to include a variety of content to cover as many aspects as possible. The record contains greetings in 55 languages, from ancient Sumerian and Hittite to modern Mandarin, English, and Swahili. Each greeting is a short message of just a few sentences, but together, they represent the linguistic diversity of humanity. Some greetings are formal, others are friendly. Some express hope for peace. Others simply say, "Hello." This was humanity's first cosmic hello. Not just one voice, but 55 different voices. But Earth was not just about humans. This is why the record also includes the sounds of nature. Thunder, the howl of the wind, the sound of rain, waves crashing on a shore, a waterfall, a stream. Bird chirps, whale songs, the trumpeting of elephants. These sounds were intended to convey the richness of Earth's natural environment, the diversity of life and ecosystems. This was the symphony of our planet. The record also contains the sounds of human activities: footsteps, heartbeats, laughter, a crying baby, a kiss, a mother's first words to her newborn child, tools being used, a saw cutting wood, a hammer striking metal, vehicles, a horse-drawn cart, a train, a car, a plane taking off. These sounds were intended to show how humans interact with their environment, how we use tools, how we travel, and of course, music. Music from various cultures and time periods was selected. Bach, Beethoven, Mozart, representing Western classical music. Chuck Berry's Johnny B. Good, representing rock and roll. traditional music from Java, Peru, Zaire, India, Japan, and other cultures. This selection was intended to show the diversity of human musical expression. Each piece of music was chosen to represent a different aspect of human creativity, different emotions, different cultural traditions. This was a playlist of the human spirit sent to the universe, but the record wasn't just sounds, it was also a picture gallery. The record contains 116 images showing scenes from Earth, mathematical and physical constants to provide a universal frame of reference, diagrams of the DNA structure, cell division, human anatomy, landscape pictures, mountains, oceans, deserts, forests, pictures of animals, insects, fish, birds, reptiles, mammals, pictures of people from various cultures, showing different activities, different ages, different environments, architectural pictures, from ancient structures to modern cities, pictures of technology, like scientific instruments, spacecraft. These images were encoded as analog signals. Each image was converted into a waveform that could be etched into the grooves of the record. To decode the images, you need to understand the encoding scheme. The instructions to do this are etched onto the cover of the record. These instructions use a symbolic language that tries to be as universal as possible. It shows the basic principles of the encoding, the scan rate, the number of lines per image. It assumes the finder has some understanding of mathematics and physics, but tries not to make too many assumptions about their specific knowledge or abilities. This was the most complex user manual ever sent into the universe, and this manual contained humanity's greatest secrets. So how will this record withstand a journey of billions of years? The record is housed in a protective aluminium cover, designed to protect it from radiation, micrometeoroid impacts, and the extreme temperature swings of space. The cover also includes a cartridge and needle for playing the record. The record itself is gold-plated to prevent corrosion, because gold is chemically inert and will not oxidize or rust, even over billions of years. The images and sounds are encoded as analog waveforms etched into the grooves of the record, just like a vinyl record. As long as the physical structure of the record remains intact, the information is theoretically recoverable. The record also contains a sample of uranium-238 in a pure form. This was included as a kind of radioactive clock. The half-life of uranium-238 is 4.5 billion years. By measuring how much of the uranium has decayed into lead, a finder of the record can determine how long ago it was created. This will tell them roughly when the Voyager mission took place, even if they can't decipher any of the other information on the record. This was a date of manufacture label left for the universe. This incredible engineering marvel, this cosmic message, this immortal artifact, accompanies Voyager 2 on its endless journey. But all this effort, all these details, all these hopeful messages. So what does this mean for us? What was the real philosophy behind such a massive effort? Now is the time to stop and think. Because the story of the Golden Record tells us much more than just about communicating with aliens. This story is actually about us. The greatest story we tell ourselves. But now is the time to stop and think. Because the real purpose of the Golden Record was never to communicate with aliens. Everyone knew how low the chances were. Space is too big. The spacecraft is too small. The record was actually a statement to ourselves. It was the idea that humanity could create something that might outlive our civilization, our planet, even our sun. It was a message in a bottle, thrown into the cosmic ocean, sent not with the expectation of being found, but as an expression of hope and curiosity, a symbol of the human desire to reach beyond our limits. And now we face the most important question. What does this machine, launched almost 50 years ago and now drifting in interstellar space, tell us about our own place? The answer to this question begins with a great paradox. On the one hand, there is the incredible achievement of humanity. We built Voyager 2, we launched it, we guided it to the farthest corners of the solar system, and now it is a man-made object that has entered interstellar space. This is a testament to the intelligence, curiosity, and perseverance of our species. But, on the other hand, There is our absolute smallness in the face of the incomprehensible vastness of the universe. Voyager 2 is travelling at 55,000 kilometers per hour, but it will take it 40,000 years to reach the nearest star, and billions of years to cross the galaxy from one end to the other. This is why there is a tragic reality in this journey. We will never see the end of this journey. Not us, not our children, nor their grandchildren. When Voyager 2 passes by Ross 248, the civilization that built it may already be history. When it reaches Sirius, humanity might not exist on Earth anymore. This is the sadness of sending an emissary into eternity who will never return. But, that word but changes everything. Because within this smallness, there is an incredible beauty. Yes, we may not be able to physically go to those stars, but with our minds, we are there. Voyager 2 is our eye, our ear, our touch. It travels in that void on our behalf, an extension of our existence. This is why you too, yes you, are a part of this incredible journey. You too are drifting in interstellar space with that small piece of metal. Because what Voyager 2 carries is not just instruments and a golden record. It carries your curiosity, your dreams, your desire to understand the universe. We are touching the universe through that machine. This is not a victory of our power, but of our understanding. And this confronts us with a second paradox: time itself. On the one hand, there is Voyager 2's journey that will last for billions of years, an almost eternal life. But, on the other hand, there is our fleeting existence. Human life is less than a blink of an eye on the cosmic calendar. When the galaxy merges, when the sun dies, when the last stars burn out, Voyager 2 will still be there, but we will not. This is why the tragic part of this journey is our transience. We are actors who take the stage for only one act of this great cosmic play. And when the play is over, we too will leave the stage. Voyager 2 will remain in that theatre like an abandoned stage prop. This is the harsh reality of existence. The time allotted to us is limited. But within this limited time lies an incredible privilege. Because we are the generation that witnesses this story. We saw the first photos Voyager sent from Jupiter. We marvelled at the complexity of Saturn's rings. We witnessed the historic moment when the heliopause was crossed. We watched live as humanity took its first step outside the solar system. This is a very special moment in human history, in a universe that has existed for billions of years. And you are a part of this moment. You are living in a time when humanity is redefining its place in the universe. Perhaps billions of years from now, other intelligent beings will explore the universe. But for them, Voyager's passage will be an ancient archaeological find. For us, it is a living legend. This is why, yes, our time is limited. But in that limited time, we have had the chance to touch eternity. This brings us to the third and perhaps deepest paradox: loneliness and connection. Voyager 2 is the loneliest object we have ever created. 21 billion kilometers from Earth, tens of thousands of years from the nearest star, completely alone. This cosmic loneliness is one of the most fundamental feelings that makes one question humanity's place in the universe. In such a vast universe, in such a silent void, are we truly alone? Voyager 2's silent journey screams this question in our faces. It is like a monument made of metal to our collective loneliness. But within this deep loneliness lies a completely opposite truth. Voyager 2 is also one of the most powerful symbols that connects us to each other, because it is an achievement not of a single nation, a single culture, but of all humanity. The engineers who built it, the scientists who guided it, the researchers who analysed its data, they were all people from different countries, different backgrounds, but they came together for a common purpose: to explore. Voyager is proof of what we can achieve when we transcend our borders, our differences, and you are a part of this connection. You too, look up at the same sky as someone in a different part of the world. You see the same stars, the same planets. Do you remember that iconic pale blue dot photograph sent by Voyager? In that photo, all our wars, all our joys, all our history is contained within that tiny blue pixel. While Voyager reminds us of how small we are, it also shows us how much we are together on that small dot. It is a common message sent from our common home. This is why, yes, Voyager 2 is lonely, but because of its loneliness, we are closer to each other. These paradoxes show that Voyager 2 is not just a spacecraft, but also a mirror. It reflects ourselves, our hopes, our fears, and our place in the universe. It is a philosophy machine that makes us question what it means to be human. But the story of this machine is not over yet, because its journey is not just forward, but also a journey back into its own past. And in that past lie incredible details about how this mission was miraculously accomplished. These details show how much we pushed the limits of human ingenuity, and more importantly, how this great adventure was saved by a hair's breadth. And the miracles in this mission were not just philosophical, but also extremely technical. Because what kept Voyager alive was not just an ingenious power source, but also humanity's most advanced engineering skills of that era. Every piece in this mission, every decision, every line of code was like a game of chess. And in this game, humanity was playing against nature's toughest rules. This is why Voyager's story is also the story of a struggle for survival. The first and greatest weapon in this struggle was the Grand Tour alignment. This was that rare planetary alignment noticed in the 1960s that occurs every 176 years. NASA engineers calculated that a spacecraft launched in 1977 could visit all 4 outer planets using the gravitational slingshot effect. But the mission was incredibly ambitious, perhaps too ambitious, because the spacecraft had to operate for at least 12 years to reach Neptune. This was a duration that no spacecraft had ever achieved before. The spacecraft had to survive Jupiter's brutal radiation environment. It had to bounce from planet to planet with precision, like a billiard ball. And most importantly, it had to operate autonomously, without waiting for instructions from Earth, making its own decisions. Because the delay imposed by the speed of light made real-time intervention impossible. This is why this mission could have ended in a tragic failure. Many people doubted it could be done. But the engineers at NASA's Jet Propulsion Laboratory were determined to try. They designed a spacecraft that was robust, reliable, and capable. And at the heart of this design lay the philosophy of redundancy. This meant that every critical system had a backup. If one system failed, a backup could be activated. This was like a safety net under a circus acrobat. They tested everything down to the smallest detail. They exposed the spacecraft to radiation, vibration, thermal cycles, and vacuum. They planned every detail of every encounter. They calculated the trajectories, timings, instrument observations, and programming sequences months in advance. And it worked. Not flawlessly. There were problems and failures along the way. The mission succeeded far beyond everyone's expectations. Both Voyager spacecraft completed the Grand Tour, and both are still operating almost 50 years later. This is a victory not just of a machine, but also of the human will that created it. But within this victory lay another paradox: knowledge and the unknown. On the one hand, there is the vast treasure trove of knowledge Voyager sent us. Jupiter, Saturn, Uranus, and Neptune were points of light in telescopes before Voyager. Voyager transformed them into living, breathing, complex worlds. It was the one that showed us those volcanoes, those rings, those storms, those geysers. This is why Voyager laid the foundation of our modern understanding of the solar system. But, on the other hand, there is the much larger ocean of the unknown that this knowledge opened up. While Voyager showed us how much we knew, it also slapped us in the face with how little we knew. The volcanoes on Io, the possibility of an ocean on Europa, the geysers on Triton, none of these were expected. Every discovery gave birth to dozens of new questions. Is there life in that ocean? What triggers those geysers? Why are those magnetic fields so strange? Voyager brought answers, but for every answer it brought, it asked 10 new questions. This is why the tragic side of this journey is that our curiosity can never be fully satisfied. The more we learn, the more we realize how vast the universe of what we don't know is. But this is also the most beautiful part of science. Science is not a destination, but an endless journey, and Voyager is one of the bravest pioneers of this journey. You too are a part of this journey, because you too are curious. You too ask questions. You question why and how. Voyager is the representative of this fundamental human impulse in space. It asks those questions on your behalf, and even if it can't find the answers, it reminds us of how important it is to keep asking. All these philosophical lessons that the Voyager mission taught us actually point to one single truth. We are a part of the universe. We are tiny, temporary, and alone. But we also have the ability to understand. We have the desire to connect. And most importantly, we have the power to transcend ourselves. Voyager 2 is a proof of this power, made of metal wire and plutonium. We now know what its journey tells us. But there is one more question, perhaps the most important one. What have we learned from this journey? What does this mission say about us as humanity? Because Voyager's legacy is hidden not just in the data it sent, but also in the deep mark it left on the civilization that sent it. And that mark carries both a warning and a beacon of hope for the future. And now we face a deeper question. What does this mission say about us as humanity? Because Voyager's legacy is not just about scientific data and philosophical questions, it is also a source of inspiration. And this inspiration has had an effect that has lasted for generations. The Voyager missions shaped a generation of scientists and engineers. Those children who saw the first images of Jupiter's moons or Saturn's rings decided to work in space exploration. The people who are leading missions to Europa, Titan, and other worlds that Voyager first showed us as interesting targets are those very children. This is why Voyager showed us that exploration was possible. It proved that we could send our instruments to distant worlds and learn about them. It showed that the solar system was accessible if we were willing to make the effort. This was opening a door, and through that door, a whole new generation of explorers passed. But the opening of this door reveals another paradox: progress and cost. On the one hand, there are the magnificent missions that came after Voyager, building on its discoveries. The Galileo mission, which orbited Jupiter from 1995 to 2003. The Cassini mission, which studied the Saturn system for 13 years from 2004 to 2017. The Juno mission, which is currently orbiting Jupiter and studying the planet's internal structure and magnetic field. And the Europa Clipper mission, launched in 2024, which will study Europa's subsurface ocean in detail. All of these missions owe a debt to Voyager. Because Voyager showed us that these worlds were worth studying, it provided the first detailed look at what was out there. But, on the other hand, there is an inevitable reality that comes with this progress. Each new mission makes Voyager a little more old. Its technology, its methods, its discoveries are now being surpassed by more modern, more capable instruments. This is why the tragic side of this situation is the fate of a pioneer. Pioneers open the way, but those who follow on the path they opened go farther than them. Voyager was once the pinnacle of technology, but now it's like a museum piece. This is a sadness that comes with progress. But within this sadness, there is an incredible pride. Because the fact that an idea, a mission, a machine can so profoundly influence what comes after it is the greatest proof of how successful it was. Voyager lit a torch, and new generations are now carrying that torch. You too are a link in this chain. Because by learning this knowledge, by listening to this story, you are carrying the light of that torch into the future. This is the immortality of knowledge and inspiration. And this brings us to another important paradox: immediate problems and long-term vision. When Voyager was launched in 1977, the world was grappling with economic recession, political turmoil, and social unrest. The Cold War was ongoing, the energy crisis was affecting world economies. Many people questioned the cost of space exploration. But NASA moved forward with Voyager. These missions were not solving any immediate problems on Earth. They were not curing diseases, feeding hungry people, or ending conflicts. They were pure exploration, driven entirely by curiosity and the desire to understand. This is why the tragic side of this situation is how focused humanity is on short-term crises. Daily problems can prevent us from seeing the big picture, from investing in long-term goals. The urgent can trump the important. But Voyager is proof that there are moments when we do not fall into this trap. Because these missions were funded, launched, and completed. This reflects that humanity is capable of looking beyond its immediate needs and problems. It shows that we can invest in long-term efforts that may not have an immediate payoff. It proves that we can do things simply because they are worth doing, because they expand our knowledge and our capabilities. You too face this dilemma every day. The stress of daily life, bills, responsibilities, all of these can prevent you from dreaming big, from being curious, from learning. But Voyager reminds you that it is possible. It shows that even in the most difficult times, we can find the time to look at the stars. Because looking at those stars is not a luxury, but a necessity. It reminds us of who we are and what we can be. This brings us back to the real philosophy behind the Golden Record. That record was not necessary for the scientific goals of the mission. The spacecraft would have worked perfectly fine without it. But it was included anyway, as a message to the future, as a symbol of hope and possibility. This was a philosophical, almost spiritual act beyond practicality. And this act contains one final paradox: silence and message. On the one hand, there is the impending silence of Voyager 2. In a few decades, its power will run out and it will fall silent forever. From that moment on, it will send no signals to the universe. Its existence will be almost equivalent to its absence. This is a symbol of our fragility in the face of the overwhelming silence of the universe. Even our loudest scream eventually fades into the void. But on the other hand, there is an immortal message it carries within that silence: the Golden Record. That record will continue to speak long after we are silent. It will say that we created art and music. It will tell that we spoke many languages and lived in many different cultures. It will show that despite our differences, we shared a single planet, a single home. It will whisper that we wondered about the cosmos and our place in it. It will declare that we hoped for our civilization to continue, to reach the stars, to make contact with others who might be out there. You too live this paradox in your own life. One day, you too will be silent. Your existence will end. But the marks you leave behind, the lives you touch, the works you create, the stories you tell, they will continue to speak. Voyager reminds us that we can leave a legacy beyond our physical existence. It shows that the most important messages are not the ones shouted the loudest, but the ones that last the longest. Voyager's inspiration, the power of long-term vision, and the immortal message within the silence. All of this explains why this mission is so much more than a pile of metal. It is a reflection of humanity at its best. Curious, ambitious, collaborative, and thinking beyond the now into the future. But this future is now completely out of our control. The spacecraft continues on its path, and at the end of that path lie not only the stars, but also the harsh realities of the mission itself. Because that end is approaching step by step, and this end is getting closer with every passing second. Because Voyager 2, even now, as we read these words, is still working. It continues to collect data about the interstellar medium. Its magnetometer is still measuring the magnetic field. Its plasma wave subsystem is still detecting radio emissions and plasma waves. And its cosmic ray subsystem, though scheduled to be turned off in 2026, continues to count high-energy particles until then. All of this data is sent back to Earth, received by the Deep Space Network, processed by mission scientists and published in scientific journals. Even after almost 50 years since its launch, Voyager 2 is still making discoveries, contributing to our understanding of the universe. But this doesn't mean the end is not coming. On the contrary, it shows how precious these final moments are. This value helps us understand another paradox: creation and destruction. On the one hand, there is humanity's ability to create this incredible machine. We designed it, built it, tested it, and sent it on a journey of billions of kilometers. This is a triumph of our creativity, our intelligence, and our collective effort. But, on the other hand, there are the inevitable laws of decay of the universe. The half-life of plutonium-238. This is a fundamental physical reality we cannot change. This is why the tragic side of this situation is the fact that everything we create will eventually be destroyed. Even our greatest monuments will turn to dust. Our greatest achievements will be forgotten. Voyager 2 cannot escape this fate. Its power source is running out, and no amount of engineering genius can change this fundamental law of physics. But, within this inevitable end, there is a comforting beauty. Because the fact that something doesn't last forever doesn't make it meaningless. On the contrary, it makes it more valuable. Voyager 2's remaining time is so precious for this reason. Every bit of data it sends is like a final whisper before an eternal silence. And you are the generation that hears these last whispers. You are witnessing the final moments of one of humanity's greatest adventures. This places a responsibility on you. The responsibility to understand this story, to appreciate this legacy, and to carry these lessons into the future. This brings us to one last paradox: memory and forgetting. On the one hand, there are those of us who remember Voyager 2. The engineers who designed it, the scientists who analysed its data, the controllers who managed its mission, and you, who are learning this story. They are slowly retiring, passing away. But their memories, their stories, the knowledge they passed on to us, lives on. Voyager 2 lives on in our collective memory. But, on the other hand, there is the inevitable forgetting of the future. One day, the last person who remembers Voyager will also die. The mission will be forgotten. It will become a line in history books, perhaps a legend. And then, perhaps, it will be completely forgotten. This is why the tragic side of this situation is that even our greatest achievements are but a drop in the ocean of time. The universe has no memory. It is indifferent. But in this indifference we understand how miraculous human memory is. We are the only beings who resist oblivion. We tell stories, we erect monuments, and yes, we send probes into space. These are all different ways of saying, we were here. And you, by listening to this story, by telling it to someone else, are keeping this memory alive. You are a resistor against forgetting. Voyager 2 may have embarked on an endless journey, but its true immortality lies in your mind, in your curiosity, in the stories you will tell. At the end of this journey, how do we feel? On the one hand, we might feel a sense of sadness at the impending death of Voyager 2, at the fragility of humanity and the indifference of the universe. This is a melancholic ending. But, on the other hand, we can also feel a deep admiration and hope at what this tiny machine has accomplished, at the potential of humanity and the power of curiosity. This is an inspiring victory, and in fact, both are true, because the story of Voyager 2 is both a triumph and a tragedy. It is proof of both how strong we are and how weak we are. It is a symbol of both how much we know and how little we understand. It is a mirror that contains all the complexity, all the paradoxes of being human. We now know that Voyager 2's final destination is not a distant star or a dramatic boundary. The place where it will die is exactly where it is right now, interstellar space. When its power runs out, when it falls into silence, it will still be on a galactic scale, just outside its home's door. We now understand that its journey gains meaning not from its destinations, but from the paths it has crossed, the boundaries it has overcome, and the lessons it has taught us. And we are now aware that the story of this machine is not just the story of a machine, but the story of the civilization that created it. This journey is ending, at least for us. The moment when the signals will be cut, when communication will cease, is approaching. And when that moment comes, all that will be left is the machine itself and the deep, unsettling legacy it has left us. Voyager carries humanity's message to the universe, but I haven't told you something. For 50 years, there has been only a deafening silence. With billions of galaxies, trillions of planets, why is everyone silent? On our next journey, we will investigate the eerie silence of the Fermi paradox and the secret of the Great Filter. Are we alone? Are you ready?